Next, we're going to talk about a class of reactions called elimination reactions. The first reaction we'll study is called an E2 reaction for an E2 mechanism. And the name of that reaction comes from the fact that it's an elimination reaction and that it is bimolecular. It is a one-step mechanism, very similar to the SN2. So the other mechanism we saw that was a single step was also bimolecular, and that has the same 2 that the E2 is, the SN2 backside attack substitution reaction. And something that the E2 mechanism needs is a strong base. So what are things that we know of as strong bases? Things like hydroxide or alkoxide, maybe an N- would also be a very strong base. Okay, so pretty short list of species that we would describe as strong bases. Those are the kinds of reagents we'll need to do an E2 elimination. And here's an example of one. Let's react, we'll start with an alkyl halide, and we'll react it with sodium hydroxide. That's a nice strong base. And what do bases do? Bases go after protons. The proton we're going to attack is located right here. It's not on the same carbon as the leaving group. Remember, the halide is going to behave as a leaving group just like it did in a substitution reaction. And the hydrogen that gets attacked is not on the same carbon as the leaving group. It's the next carbon over. So we call this not the alpha position, but the beta. This is called a beta hydrogen. The hydroxide, or whatever strong base we're using, is going to come in, and in a single step, it's going to grab that proton, form a pi bond, and kick off the leaving group. So the product we're going to get will be an alkene. We're going to get an alkene product. We're going to be forming a carbon-carbon double bond as a result of an elimination. The other products that are being formed, if I use hydroxide, I'm also forming water, the conjugate acid of hydroxide. And of course, I always lose my leaving group, so I also form bromide as well. So this is described as an elimination reaction because you have eliminated both the beta hydrogen and the leaving group. So we lost HBr, so sometimes this reaction is described as a dehydrohalogenation because you've lost the hydrogen and the halogen. What do you think an energy versus POR diagram would look like? Well, it would be a lot like our SN2 mechanism because that was also a single-step reaction. Our energy versus progress of reaction, we would start at some combined energies for our starting materials, the hydroxide, the alkyl halide. We're going to end at some final product energy. Okay, assuming it's a favorable reaction, that's going to be an exothermic reaction. And in order to get from the starting material to the product, as usual, for our one-step reaction, we're going to go through just a single transition state to go here. So really the energy diagram looks very similar to that for the SN2. And what does the transition state look like? The transition state has a lot of bonding changes taking place all in a single step. First of all, we're forming a new bond between the hydroxide and the hydrogen. So forming bonds we show as partial bonds in the transition state. We're also breaking this carbon-hydrogen bond. So breaking bonds we're going to draw as a partial bond in the transition state. Let me draw the rest of my carbon chain here. We are also forming a pi bond between these two carbons, so we'll show a partial double bond being formed between those two. And finally, our leaving group is leaving, so we're breaking the carbon-bromine bond, and we'll draw that as a partial bond as well. So 4 bonds involved in this mechanism being formed or broken. And how about any partial charges that we need to account for in our transition state? In our starting materials, our oxygen is negatively charged, but it's neutral in the product, so that charge is disappearing. We have a partial minus on the oxygen. And our bromine starts out neutral but ends up as bromide, so we have a negative charge developing on the bromide. So that's what our transition state looks like for the E2 elimination mechanism. What about the stereochemistry for the E2? If we're dealing with a chiral molecule and we have some asymmetric centers, what is the ramification of that stereochemistry when we do an E2? Well, it turns out that there's a special relationship we have to have between the beta hydrogen and the leaving group that got eliminated. They need to be anti-coplanar. That's the relationship we described when we looked at Newman projections. We said two groups were anti if one was straight up and one was straight down, right? Or anytime they have a 180-degree dihedral angle. So that is the required relationship of the leaving group and the beta hydrogen. And for that reason, the E2 is described as anti-elimination. So let's see an example of this. Here we have, I had to hand rush some of this. We have an alkyl halide. Here's our leaving group. That's going to be eliminated. And we're not just eliminating a leaving group. We also have to eliminate a hydrogen on the next carbon over. We go to this carbon. We see there are no hydrogens. So we go to the next carbon, and here we find there's only one possible beta hydrogen. Okay, but when we look at this conformation as drawn, the H and the Br are not anti to one another, but they're both dashed bonds, dashed lines. So if we were to look at this from the side, we see that they'd be gouged to one another. They're close to one another. So, but that's okay. This is a molecule that can be rotated. We can rotate around that carbon-carbon single bond, and that's what we'll do. We're going to rotate first and rearrange it such that the hydrogen and the bromine are 180 degrees. So one way to draw that very easily is to show the hydrogen pointing straight up, the bromine's pointing straight down, both in the plane. That must mean they are anti-coplanar. So now, for the next two drawings, we see the H and Br are anti, and that is the necessary conformation. We have to do this. We have to be able to do this before we can do the E2 elimination. But if we're going to rotate this, that's going to move these other groups. Where are they going to go? Okay, well, let's start with, let's look at this bromine. And I built a model of this. Okay, so this bromine right now is pointing away from us. It's a dashed line. What we need to do is we need to rotate it into the plane. Then we need to bring it forward. Now, what does that do to this phenyl group? It was in the plane, but when we rotate it, it's like we grab onto this group and turn all three groups clockwise. That pushes the phenyl group backwards. And so on this carbon now, the phenyl is going to be a dash bond, and this hydrogen was a wedge. It's still a wedge. It was pointing down a little bit, and now it's pointing up a little bit, but it's still pointing towards you. Okay, let's see if we can do this second carbon. We want the hydrogen to be pointing straight up and in the plane. So what did we have to do? We had to grab onto that hydrogen and bring that forward as well. So we grab onto that molecule and twist that carbon. What's going to happen to this ethyl group? Is it now going to be a wedge bond or a dash bond? Well, let's take a look. Here's our drawing. Our ethyl group is in the plane. Our methyl group is a wedge. Hydrogen is a dash. We want to bring this forward so that it's in the plane. And when doing so, that's going to push our ethyl group back. So the ethyl group will also be pointing backwards. CH3, CH2. And our methyl group is still a wedge. So we're going to need to manipulate our molecule a little bit to get the leaving group and the beta hydrogen anti to one another. Another perspective of this drawing is if we stand here and look at it this way. Okay, on this front carbon, we see the hydrogen pointing straight up. On the back carbon, you see the bromine pointing straight down. So this is that relationship of anti that we described back when we first learned about these Newman projections. Okay, so once it's in the proper conformation, now my base, whatever base I'm using, can come in and do the elimination. 1, 2, 3 arrows. Grab the hydrogen, form the pi bond, kick out the leaving group. And what happens is because it is a concerted mechanism, all the other groups that are on the carbon chain end up getting frozen in place, the relative positions they were in this anti-conformation. So notice that the phenyl and the ethyl are on the same side here. After I do the elimination, the phenyl and the ethyl are required to still be on the same side. I can see it in this drawing too here. The ethyl is a dash, the phenyl is a dash. They're both behind the page. So when we flatten it out, remember when we do the elimination, we're going to a planar product. So everything is going to be pushed up or down a little bit, but the phenyl and the ethyl are still going to end up being on the same side. So this is going to be the only stereochemistry that's observed. In other words, we're not getting this possibility where the ethyl and the hydrogen are on the same side. This product would arrive from a different conformation and one that does not have the hydrogen and the bromine anti originally. So let's try another example. Here we have two phenyl groups. Let's identify our leaving group. That's always easy to find. It's going to be a halide, maybe a tosylate, but a halide would do great. And where do we have our beta hydrogen? This is another example where there's only one possible beta hydrogen right here. And so are they anti right now? They're not anti right now. They're both dashes again. So let's rotate this. The easiest way to rotate this compound would be to bring that bromine slightly forward, bring that hydrogen slightly forward, so that they're both in the plane with one up and one down. Now let's fill in our dash and wedge that we know are here and see where those phenyl groups go. So what do you think? This bromine, when you bring that bromine forward, what does that do to the phenyl group? If you bring the bromine forward, that's going to push the phenyl group back. And when you bring this hydrogen forward, that's also going to push this phenyl group back. So this is the proper conformation that we have where they are now anti to one another. So what we did here was we just rotated so that they are anti. And now we could have our base come in and do our elimination. 3 arrows. Base attacks the hydrogen, forms a pi bond, kicks out the leaving group. Since it's just a one-step mechanism, it's a great idea to go ahead and draw the arrows so you have a better chance of drawing the product accurately. And we're going to get an alkene product, which is planar. And what is the relationship of those two phenyl groups going to be? Because they are both behind the board. One is a little up and one is a little down, but they're both going to get flattened out, but they're both still going to be behind the board. So whether you draw them on the top or the bottom doesn't matter, but you need to show them on the same side of the double bond. So we have two phenols on the same side, and what are the other two groups? We have a methyl and a hydrogen. Those were both wedges pointing out toward you, and they still will be. Okay, so and again, doesn't matter if you draw the phenols up or you flip it over and you draw the phenols down. That's the same exact product. So anti-elimination is the way we describe the stereochemistry of the E2 mechanism. What about the regiochemistry of the E2? Regiochemistry is when we ask about what region or site reacts. So if we have a choice of more than one site on a molecule to undergo reaction, how do we make that decision? And here's such an example. Here we have an alkyl halide. We see our leaving group. We treat it with a strong base. Let's say we want to do an E2 elimination. Actually, I think there's more than one possibility here. So let's consider both possibilities. If we wanted to do an E2, we have our leaving group is on this carbon. Where do we have beta hydrogens? Well, we have a hydrogen on this carbon. And on this carbon, we have two hydrogens. We have one that's a wedge and one that's a dash. Okay, so the hydrogen on the far left, we'll call that HA. And the hydrogen that's a dash, we'll call that HB. And let's call this D. I'll refer to that hydrogen in just a moment. And what's another thing that can happen? Let's think about this, starting with this reagent that we're using, hydroxide. What do you know about hydroxide's reactivity? What can it do? Is it an acid or a base or an electrophile, a nucleophile? Well, it certainly can be a strong base. And that's what we're considering right now, doing the E2 elimination as a strong base and attacking a proton. But isn't it also a strong nucleophile? It definitely is, a strong nucleophile. What mechanism do we associate with strong nucleophiles? Backside attack, SN2 mechanism. And so another thing that hydroxide can do is it can attack in this position Let's call that path C, and that would be an SN2 path. That would be a backside attack path. So let's look at what those three products would look like, A, B, and C. A, if I took this hydrogen, would end up with a double bond between these first two carbons. B, if I took the hydrogen from this middle carbon, would give me a double bond between these middle two carbons. Now, I went ahead and took that hydrogen and left the carbon chains where they are, because notice this HB is a dash and the bromine is a wedge, so they're already in the anti-conformation, so I don't have to do any rotations. Okay, if I wanted to take hydrogen D and do an elimination there, what I would have to do is I would have to twist the molecule to get those two, the hydrogen and the bromine anti, and that would give product D. Like this. D isn't even formed, but we'll draw that up here so you can see what that looks like. And what does product C look like if you do the SN2 mechanism? Backside attack. That means you replace your leaving group, substitute your leaving group for your nucleophile, and tell me about the stereochemistry of that reaction. Since the bromine is a wedge, the hydroxide must have come from behind, and you would get a dash here. Okay, and these are in fact the three major products. 16% of A is isolated, 75% of B, and 9% of C. So SN2, we get a very small amount here, and we're going to talk a little bit later about how we would make that prediction of the E2 versus the SN2 mechanism. But of these are both E2 eliminations, but there's a huge difference on which is the major product. B is favored by far. Okay, and why is that? It's the major product because it's the more stable alkene. This is known as Zaitsev's rule, and Zaitsev's rule states that when you have a choice between different alkenes that you can form, you're always going to want to form the more stable alkene. So can you tell between B and D why B would be favored over D? Why is that the major product? Let me fill these in. Looks a little better. Why is B better than D? Well, this is cis versus trans, and the cis is going to have some steric hindrance, so that's definitely going to be less stable than the trans. So that explains why no D was formed, even though it's a possible product. Okay, but other than cis and trans, what are some other ways that what are some other things we should know about alkene stability? If we want to if we want to predict which is the major product, we have to understand which alkene is more stable. So let's take a look at some factors that will affect alkene stability. Okay, one thing is that if you are ever given conjugation, if it's ever possible to be conjugated, that's going to be a more stable alkene, more stable diene. So if you have multiple pi bonds, then it's better to have those double bonds alternating, double bond, single bond, double bond, than isolated. Here they have no relationship to each other. Here they have one right after another. We have a p orbital here and a p orbital here, and right away we have more p orbitals. This relationship is more stable because we can have resonance delocalization of these pi electrons. Okay, so if you happen to already have a double bond in the structure, when you go to form a second double bond, if it's possible to put that new double bond in conjugation with the original one, that would be a good thing. Okay, another rule is that as you increase the number of alkyl substituents on the double bond, you increase stability. Now, what do I mean by alkyl substituents? These are the number of carbon groups on the carbon-carbon double bond. Now, what's the maximum number of carbon groups that you can put on a carbon-carbon double bond? Remember, each of these carbons wants 4 bonds. So there's 2 bonds over here and 2 bonds over here. That would be a very stable carbon-carbon double bond. Let's take a look at some examples. Okay, here is one such example of that. This alkene has 4 alkyl groups attached. We describe this as being tetra-substituted. It is called a tetra-substituted alkene. That's the most alkyl groups you could possibly have. And this is the most stable alkene that there is. It really likes having those alkyl groups on there. That's going to be more stable than an alkene with just 3 alkyl groups. We call those tri-substituted. That's more stable than any dye-substituted pattern. And look at all these possibilities. These are all dye-substituted. But within the dye-substituted patterns, we want to know that the trans arrangement, where the two alkyl groups are as far apart from each other as possible, that's going to be the best arrangement. That's more stable than cis. Cis is not so good because it has some sterics here. Remember, there's some steric hindrance in cis that makes it less stable, higher energy. And that's not such a great arrangement, and this one isn't so great either. This is called geminal, or gem for short. And having a double bond, two groups on just one end of the double bond is not a very stable arrangement. And I usually don't care too much on trying to compare these two, but for sure you should know that neither of these is as good as the trans relationship, but typically cis is better than geminal. Okay, and all these are better than having just a single alkyl group. We would describe that as a mono-substituted alkene. Okay, or you could also describe it as terminal. It's called a terminal alkene because it's at the terminus. It's at the end of a carbon chain if it has just one alkyl group on it. And that's not a very good arrangement for alkyl groups as well. This is the least stable. Okay, so it turns out that this is the same general trend in stability we saw for carbocations. Carbocations like to have alkyl groups attached. That one is a little easier to understand or maybe predict because it's an electron deficient species. So why is it that alkyl groups also like to have, why is it alkenes also like to have alkyl groups attached? That discussion of that stabilization is a bit beyond our scope here. So we simply need to know that the more alkyl groups we have, the more stable it is. So let's take a look at a few examples, see if we can apply Zaitsev's rule. Here's an example. Draw both E2 products and select the major. So we have our leaving group here. How is it possible to get two different E2 products? Well, let's look for our beta hydrogens. There's no hydrogens on this carbon. It's the next carbon over. We could grab one of these hydrogens or one of these hydrogens. Would those give two different products? Actually, those would both give the exact same product. So beta hydrogen type A is going to be right here or right here. So where is the second type of beta hydrogen? How about going in this direction right here, going to this methyl group, beta hydrogen type B. So product A would form a double bond within the ring, okay? And like I said, whether you go to the right or left, it's the same product. Tell me about this methyl group. Is that still a dash? Is that still pointing behind the board? Remember what an sp2 hybridized carbon looks like, an alkene carbon? This is planar, and so that methyl group now after the elimination is completely flat, and it should be drawn as a straight line. So now you can see that if you just flip it over, taking the hydrogen from either side would give the exact same product. Okay, but what's the other possible product we can form? Instead of going to one of the side ones, we can go up to this top carbon, and what does he look like now? He used to be a CH3. It's now going to be a CH2 because one of those hydrogens was taken away. So these are the two possible products we can get. And now which is the major product? We're going to look to see which one is more stable, and for that we're going to see which one is more highly substituted. How would you describe this the number of alkyl groups attached to this first carbon, to this first alkene? Here's our alkene. We have 1, 2, 3 carbons attached to it. In other words, there's only one hydrogen. So this is a tri-substituted alkene. And how about the second one? We have 2 hydrogens up here and 2 carbons. So we're not counting the carbons in the double bond. We're asking how many carbons are attached to those double bonds. This is a di-substituted alkene. And so which would be the major product? The tri-substituted would be the major. Okay, why? Okay, it's usually not such a great idea to just say because Professor Zaitsev told me so, right? Or just invoke the rule. The reason it's the major product is because it's the more stable alkene. So that's how we determine the regiochemistry of an E2 elimination. Let's take a look at another example. If our leaving group is part of is attached to a 6-membered ring, now it's the chair conformation of that compound that needs to be taken into consideration when we look at the stereochemistry and the regiochemistry. Here again we have a strong base. We forgot to mention that up here, just noting we are using hydroxide. Now here we're using methoxide, also a strong base. And when we look at it in this conformation, if you think about where you're going to take your beta hydrogen, we have hydrogens over here, we have hydrogens over here. Now which one is more tempting to take based on Zaitsev's rule? So for regiochemistry, where do you think you want to go? I'm guessing we might want to go to this side because that would give us a more highly substituted double bond. But there's a problem with that. What did we learn about the stereochemistry of the E2? Let's draw in that hydrogen and see if you can find a problem with that hydrogen. That hydrogen is a wedge, that bromine is a wedge. Is it possible to rotate that to get them anti to one another? It's not. So because this is not anti, I can't eliminate in that direction. Instead, I have to look over to this side. This is a CH2. One is a wedge and one is a dash. This is the only anti-beta hydrogen. So there's only one possible product we can get. Now when you look at the chair conformation, the most stable chair conformation here has a bromine up. We can put that in an equatorial position. And it has a methyl down. We can also put that in an equatorial position. So the most stable chair has a leaving group in an equatorial position. Unfortunately, the hydrogen we want to take next door is not anti. Those are not anti to one another. Again, those are going to be gouged to one another when you take a look at that Newman projection. So what we're going to have to do is we're going to have to flip our chair into the other conformation. And let's see, that means we're taking this carbon and bringing it down. So that's down here. This hydrogen is now pointing straight down. This carbon got flipped up, so my bromine up is now axial up instead of equatorial up. And this carbon has my methyl group down. It was equatorial, and now my methyl group down is now axial. In this chair conformation, now my H and Br are now anti. We call it anti-diaxial. As the necessary conformation in a chair conformation, the leaving group must be in an axial position in order to be 180 degrees from the beta hydrogen. Okay, and so our base can come in, grab that proton, kick off the leaving group. And what does our final product look like? We can go back to our line drawing here. We're going to form a double bond on this side, and our original methyl group is still there. And that's the only possible product we can draw. So really this product was really just a question of regiochemistry only in order to draw the product, but I wanted to point out that the required stereochemistry requires a specific conformation of our chair, and that's going to be relevant because depending on the substitution pattern throughout the chair, this chair flip might not be such an easy thing. So you'll find that some cyclohexyl halides are do very fast E2 eliminations. Some are very, very slow. And this is an important thing to take a look at when you're considering such cases. So now that we know what an E2 mechanism looks like, let's consider its competition with the SN2 mechanism. The SN2 mechanism was described as backside attack. And what's required for the SN2 is that it needs a strong nucleophile. So in an SN2 substitution, a strong nucleophile attacked the carbon, kicked off the leaving group. That backside attack, we needed a strong nucleophile. Okay? Another thing that was very important with that backside attack was something about steric hindrance. Remember that backside of the carbon had to be very accessible. And so let's just write that steric hindrance. So it needs a strong nucleophile. and steric hindrance is bad, is not a good thing. That slows down the reaction. Okay, and what do we know about the E2 mechanism? What does it require? E2 is when we have something attack a beta hydrogen and form a pi bond and kick out a leaving group. So we're attacking a hydrogen. The E2 needs a strong base. It needs a strong base. And it turns out that this deprotonation reaction is not affected by sterics. So the sterics is going to be a major factor in making the decision between an SN2 and an E2. We'll see. So when do they compete? When do we have to make this decision? Well, most definitely we're going to see it for reactions that involve hydroxide, or so that's HO minus, or RO minus, that's known as alkoxide. So in other words, we can have methoxide, ethoxide, propoxide, so an alkyl group with an O minus. Okay, what's special about these species is they are both strong nucleophiles, meaning they love to do backside attack, they're great for an SN2 mechanism, and they're strong bases, meaning they can also go after a proton and do an E2 elimination. So we really need to be on the lookout when we're using hydroxide or alkoxide, and we'll have to make a decision between the E2 and the SN2. So let's compare some rates. If we took a variety of alkyl halides and treated them with sodium methoxide and ethanol, we could have either a substitution reaction take place. What would the product look like if ethoxide decided to act as a nucleophile and do a substitution? That means instead of RBR, we have our ethoxy. So our nucleophile has replaced the leaving group. That's our SN2. Why don't we draw out the ethoxy here? So I'll do some more abbreviations on this page. It's real good to start getting familiarized and seeing back and forth between these abbreviations. So this would be our SN2 product. What would it look like if we did elimination instead? Well, that, of course, is going to depend on which alkyl group we started with. But let's just say plus some kind of alkene or mixture of alkenes. In other words, we could do an elimination and form a double bond instead. So let's take a look at these series of alkyl halides and see and try this reaction and see what product composition we get. So the first one we have here is methyl bromide. So we could just abbreviate this MEBR for methyl bromide. And what kind of carbon is bearing the leaving group in this case? It's simply just a methyl group. We just describe it as a methyl group. This next one has 1, 2, 3, 4 carbons. You could call that a butyl bromide or N-butyl bromide, since it's the normal butyl group. And what kind of carbon is bearing the leaving group here? Well, because we have just one carbon group attached to it, we describe that as a primary carbon. This next one is another common arrangement of 4 carbons. When we have something that kind of looks like the isopropyl group here, but you have an extra carbon, this is called the isobutyl group. So if we had isobutyl bromide, this is still primary, but right next door to that, on the beta carbon, the next carbon over, we have some branching. So let's call this primary with beta branching. Okay, the second one, this 3 carbon arrangement with the attachment at the middle carbon, that's the isopropyl group. So this is isopropyl bromide, is an example of a secondary carbon bearing the leaving group. And then once again, we come back to good old T-butyl bromide. Tert-butyl bromide is just kind of a classic example of a tertiary carbon bearing a leaving group. So what have we done? Why have we chosen this series of compounds? Because as we move down this list, we see that we are increasing in our sterics. We have increasing sterics about the carbon bearing the leaving group. And what proportion of products do we see as a result? Well, when we have methyl bromide, it turns out that we see 100% SN2 reaction, no E2 at all. Now let's think about what that E2 product would look like. What does E2 mean? It means you remove the leaving group and a beta hydrogen, and you form a carbon-carbon double bond. So how does that look for methyl bromide? It's looking pretty impossible because not only does it not have any beta hydrogens, it has no beta carbons. So this is, let's just put Na here because there's no beta hydrogens. You can't form a carbon-carbon double bond if you only start with one carbon. So of course we expect 100% for SN2. Okay, but when we move to primary, now the E2 is possible, and we do get a mixture of the two, but it's heavily in favor of the SN2. We get about a 90-10 mixture. So almost all SN2, but we start to see a little bit of the E2 side product. Adding just the slightest bit of beta branching here, so the slightest bit of sterics, now pushes it in the other direction where the elimination is favored. That's just how sensitive the SN2 substitution, that backside attack, is to steric hindrance. And in fact, if we go to a secondary carbon, then it is favored in the opposite direction even more so, where E2 is the major product by far, 4-1. So now we're really shifting. And how about tertiary? What do you think about the tertiary SN2 reaction? Does that look like a good reaction? No, we know there's way too much steric hindrance here. So let's say there's essentially 0 and 100 now in this switch. Remember, tertiary alkyl halide is no reaction with the SN2. Okay, and so it's no reaction with the SN2, but a reaction, in fact, does take place. Instead, it's the E2 elimination reaction. So let's continue looking at this comparison and come back to tert-butyl bromide. What we're asking it to do when we react it with ethoxide or some other strong base that can also be a nucleophile is it has two choices. It can either attack the beta carbon, attack the carbon bearing the leaving group, do a backside attack, that's the SN2 path, or what can it do? It can attack the beta hydrogen, that's the E2 path. Attack the beta hydrogen, form the pi bond, kick out the leaving group. Okay, and which of these is possible for the tertiary center like T-butyl bromide? The SN2 is impossible. It's impossible to get in here with all this steric hindrance to do backside attack. But look how accessible that beta hydrogen is. You can see that sterics is not going to be a problem anytime we're going after tiny little hydrogen. Eliminations are no problem. So let's just make a note here that the backside attack is too hindered. And that the beta hydrogen is more accessible. So we get 100% E2 with a tertiary leaving group. Okay, that's kind of the ultimate in the examples of SN2 versus E2. Okay, now another possibility is to vary the base that you're using. What if you had a primary alkyl halide? Okay, here we have 15 methylene units, 15 of these carbons, so it's just a really long carbon chain with a bromine at one end. And what if we reacted this with a species that could be either a base or a nucleophile? What kind of mixture do we get distribution between SN2 and E2? Well, if we use a small base like methoxide, what we see, the same thing we just saw on the previous slide, is that SN2 is favored because there's very little steric hindrance for a primary carbon, and we get something like 96% of the SN2 and maybe just a little 1% of the E2. However, if we use this guy, what is this structure? That's a strange looking structure. Well, remember, potassium is just a K+, so that means we have O-, and this is the T-butyl group. T-butyl group. So this could be abbreviated as TBUOK. TBUOK is potassium tert-butoxide. When we have a very, very bulky base now, that's going to hinder that backside attack, and we see a push in the other direction, and now elimination can be favored. So this guy, he's called T-butoxide. He's a very bulky base because he brings along with him that T-butyl group. I brought some models here again just as a reminder about the sterics like we're seeing here. You know, the methyl is so tiny, but the tert-butyl, when you have 3 methyl groups attached to a carbon, that really inhibits this backside attack. Okay, and now if we're thinking about this coming in and acting as a nucleophile, this is going to have the same problem. This is going to have a hard time getting in to do a backside attack on a carbon-bearing leaving group because it's bringing steric hindrance with it. So T-butoxide is a very bulky base, so it's never good for an SN2 unless maybe you're attacking a methyl group that can't do an E2. And so really these are classic E2 reaction conditions. If you really want to favor an E2 elimination, then T-butoxide is a great base to choose. Okay, by the way, addition of heat also favors elimination, so we should get used to seeing heat as part of the reaction conditions. That's because we're breaking the molecule up into different pieces, so that's going to favor the entropy of the reaction. So elimination reactions are also usually done in the presence of heat. So let's summarize. What would we say the preference is for E2 over SN2? So looking at a reaction type, which type of alkyl halide would really like to do the E2 elimination? Well, the tertiary is going to be the best. This is pretty much all E2 and no SN2 at all. Okay, secondary still prefers E2, but you know, you're going to have a little substitution. Okay, and here's where we see that big jump when we're looking at primary. This now is essentially all SN2. Okay, so only if it's a primary alkyl halide can you still expect to do an SN2 with a strong base. As soon as you get to secondary, and of course if you're at tertiary, if you take a look at that data from the previous slide, you'll see that E2 is now the major product. So only when there's absolutely no steric hindrance because you have a primary leaving group. And of course, we're leaving off the methyl here intentionally because methyl has no beta hydrogens. That would be impossible to do the E2 in that case. So let's take a look at a second elimination mechanism. We saw the E2 elimination, which is the one-step mechanism. Base attacks a beta hydrogen, forms a pi bond, kicks off the leaving group. Another mechanism that we can have for doing a dehydrohalogenation, losing a hydrogen and a halogen, is an E1 mechanism. That stands for elimination unimolecular. Okay, and let's take a look at an example of that. If we take this alkyl halide and we treat it with water, how would we describe water as a reagent? Well, water is a weak nucleophile. It's weak everything. It's a very stable molecule. So it's a weak nucleophile. It's a weak base. But we can still undergo substitution elimination reactions here. In fact, we do get a substitution product. Now, would you expect that substitution to occur by SN2 mechanism, backside attack? No, because this is such a weak nucleophile and because this is a tertiary leaving group. So this can happen by SN1. And it's also possible to get some elimination product. Now, could this elimination be the one-step E2 mechanism? No, because we don't have a strong base. So instead, a different mechanism must be in operation, and it's the E1. So the SN1 and E1 we'll find are always in competition. Just like we saw the E2 and the SN2 are often in competition, can be in competition, the same is true for SN1 and E1, these unimolecular reactions. And the SN1 is usually the major product. In most of the reactions we're going to see there will be a nucleophile around. It is going to prefer to add, and so we'll get the substitution. Okay, so E1 is maybe a side reaction. So you might see a little bit of elimination, and this is how you get it. We'll see one example where the E1 is the primary mechanism in action when we do the dehydration of alcohols. But with that exception, SN1 will be major. Okay, and the mechanism for an E1 is going to be two steps, and it's going to be via a carbocation. Again, very similar to SN1, that's why they compete. So our first step is going to be loss of a leaving group. Our chloride is going to leave, which results in a carbocation intermediate. So notice this is the same slow rate determining step as SN1. So I lose my leaving group, and I form a carbocation. And but now, instead of having that carbocation get attacked by a nucleophile to do a substitution reaction, instead we can do an elimination. Now, what did it mean to eliminate? You eliminate a leaving group plus a beta hydrogen. So what have we done so far? We've lost our leaving group. So what's next? We lose our beta hydrogen. And we have a word for loss of a proton. We call it deprotonate. So we're going to take our carbocation. We're going to take a look at one of these beta hydrogens, and we're going to eliminate that beta hydrogen. So some base comes in. Again, you can use chloride if you want. I think water is a better choice because that's going to be our that's going to be formed. That's going to be present in this reaction as well. And it's your solvent, so you have more of that around. So we're going to do a deprotonation. We grab the proton. Why can carbocations get deprotonated so easily? Because when you fill in those electrons as a pi bond, you're going to get rid of the carbocation. You're going to add a new bond and get to a stable alkene product. Okay, and now let's consider the regiochemistry. Why did I select this beta hydrogen? I mean, we did see that that's the major product. But is that the only beta hydrogen that's available? Here's our carbocation. No, this is a beta hydrogen. This is a beta hydrogen. I could have also made this product. But why was that not listed as one of the products formed here? This is actually not formed. How would we make that decision? Well, it turns out that this elimination also follows Zaitsev's rule, just like the E2 did, and we're going to get the most stable alkene possible. So this would be a tri-substituted alkene. That's going to be more stable than a di-substituted alkene, and so as usual, we're going to go for the more substituted beta hydrogen to get the more substituted alkene. Let's take a look at the kinetics for the E1 mechanism. Because it had the same slow rate determining step as the SN1 mechanism, it has the same rate expression. The rate is proportional to simply the concentration of the alkyl halide, and that's all you need to lose your leaving group. And so that's why it is described as unimolecular, like SN1. The E1 and the SN1 are both referring to the fact that just a single species is present during the rate determining step, and it's directly proportional to the rate of the reaction. Its concentration is directly proportional. The rate is not dependent on the concentration of water. It doesn't matter how much of that base we have in there. It won't affect the rate. So that also reinforces the fact that water is not involved in the rate determining step, or whatever base you have. It's simply the loss of the leaving group from the alkyl halide. Okay, how can we speed up this reaction? Well, once again, the more faster, the more stable the carbocation you have, the faster it's going to be formed. So if you bring down the energy of your carbocation intermediate, that's going to have a lower energy transition state as well, and you have a lower energy of activation, faster reaction. And now, again, the faster the carbocation is formed, once you're at that carbocation, you can now do substitution or elimination. So the same thing that speeds up the SN1 reaction is also going to speed up the E1 reaction, and we come back to that competition. So the E1 rate is exactly the same as the SN1 rate. Looking at the type of carbons bearing the leaving group, these are all great carbocations. So they're going to be fast E1 eliminations. Allylic means you have an allylic carbocation. So in other words, an allylic leaving group, let's put a chlorine here, right? That would be a great substrate to do an E1 elimination, just like an SN1 elimination. Benzyl means that you're next to a benzene ring. So a leaving group next to a benzene ring would be great because that would be a stable, resonance stabilized carbocation. And then of course tertiary is what we just looked at because that's also a good carbocation. Those are better than secondary, and this is where we have our huge jump for carbocations. Primary and methyl are so bad. These are poor carbocations. So it's going to be a very, very slow E1 elimination. Okay, and actually let's cross out that methyl again because you can't have an E1 elimination with just a methyl halide because you don't have a second carbon to form the carbon-carbon double bond. How about the stereochemistry of the E1? Is there any kind of relationship that we need to have between the leaving group and the beta hydrogen? Remember E2 elimination, what did we need? Our leaving group and our beta hydrogen had to be anti to one another, one up and one down. They had to be anti-coplanar 180 degrees. Well, remember the E1 mechanism is a stepwise mechanism that goes through a carbocation. The carbocation is a chiral, it's planar. So this is another case where we're going to see loss of stereochemistry. This is the same story we had for the SN1. Remember we described it as racemization because we were dealing with chiral carbons in that case. Here we just describe it as loss of stereochemistry. So let's see an example. If we take this substrate and we treat it with a strong base, hydroxide, strong base, what does that do? That's going to come out and attack. This likes to do E2. Well, let's just kind of define it. Hydroxide is a strong base, and it's a strong nucleophile. So as a strong base, what mechanism can you do? E2. As a strong nucleophile, what mechanism can you do? Backside attack, SN2. Okay, which one's going to be favored in this case? Well, we take a look at the carbon bearing the leaving group. It is a secondary carbon. Secondary, E2 is going to be favored. Okay, we add in a little heat. That doesn't hurt. But even without that, with secondary, we're going to go with E2. There's just too much steric hindrance to do the backside attack instead. Okay, and we've conveniently drawn it already so that the hydrogen and the leaving group are anti-coplanar. So we could come right out and we don't have to rotate at all. We could just take our hydroxide, grab the proton, form the pi bond, kick off our leaving group. That's going to give us an alkene product. And what groups are going to be on the same side? You have a phenyl that's a dash, and you have a methyl that's a dash. Since those are both on the same side of the alkyl halide, they'll be trapped on the same side of the alkene. Doesn't matter whether you put them at the top or the bottom. The important thing is they just need to be on the same side. And what other two groups do we have? We have a methyl and a hydrogen. So those are still on the structure. And remember, because this is anti-elimination, this is our only product. It requires those two groups to be anti, and so this would be the only possible stereochemistry. Now let's compare this same starting material, and let's just react it with water. No hydroxide, so now we have a weak base and a weak nucleophile. What kind of reactions are possible there? Is a weak base going to go and attack a beta hydrogen? No. Is a weak nucleophile going to go and attack, do a backside attack, and kick off a leaving group? No way. So this water does reactions like SN1 and E1. And of course, the E1 is probably going to be major. Okay, the SN1 is probably going to be major, but let's take a look at the E1 to see what its stereochemistry would be. Okay, and what's going to happen here is because we have no strong base or strong nucleophile, the only other thing that can happen is the leaving group can just leave on its own. So that's exactly what happens. And when that chlorine leaves, the resulting carbocation is now planar. It's flat. And so when we go to deprotonate our beta hydrogen, the beta hydrogen can be removed now, or we can have some rotation, right? It can rotate here. So there's nothing, there's no longer anything trapping these two methyl groups into the transposition. It can rotate around. Because it's a multi-step mechanism, we lose that stereochemical relationship. Once that leaving group leaves, it's gone. So now when water comes in and deprotonates, we now have a mix of relationships between these methyl groups. And so we're going to get two products. We're going to get the one where the phenyl is on the same side as the methyl. And we can also form the one where the methyls are on the same side. Okay, you're going to get a mixture. And of course, you're also going to get SN1. And SN1 is actually going to be your major product probably. But you know, we just want to look at our E1 product composition here. Okay, so these are both possible. Does that mean they're going to be formed in equal amounts? Well, remember, Zatev's rule is still holding true. We still want to form the most stable alkene possible. So is there a difference in this case in their stability? Well, the phenyl group, remember, is a benzene ring. That's going to be larger than a methyl group. And so this product has more steric hindrance than the other one. So this is going to be our minor E1 because of sterics. And this is going to be our major E1. So, you know, for anti-elimination, we only have so much say on which alkene we can get. It has to be from anti-elimination. With an E1 elimination coming from a carbocation, we can rotate around and get to the most favorable carbocation conformation, which leads to the most favorable transition state, leading to the most stable alkene product. Let's talk just a little bit about carbocation rearrangements, because like the SN1 mechanism, we're going through a carbocation, and that means carbocations can rearrange. And so let's just briefly review what we saw for this SN1 mechanism. This was a rearrangement when our leaving group left. It gave a secondary carbocation, and that secondary carbocation could have a hydride shift to give a tertiary carbocation. That would be a favorable rearrangement. And so that's how we could get this substitution product where the nucleophiles come into a different position. And what is important to remember is that this new carbocation can also undergo E1 elimination products. And so sometimes our double bond is going to end up in a different place from where our leaving group used to be. And because both of these mechanisms deal with carbocations, and carbocations can rearrange, a lot of times we can get some very interesting product mixtures. So these end up becoming excellent practice problems for mechanisms. In other words, how can this combination of reaction conditions lead to all 1, 2, 3, 4, 5 of these products? Okay, and so this is definitely a reaction that looks like it's coming from a carbocation, because that, you know, there's the carbon chains have rearranged, the positions of the substituents have rearranged. And this is another example where our initial secondary carbocation can reorganize itself to become a tertiary carbocation. In this case, it's by rearrangement of one of these methyl groups, a shift of a methyl group. Now, if this carbon group moved over here, that carbon is now has lost its carbocation. It's got 4 bonds again, but this carbon is where the carbocation is now. And so hopefully you can see how that can lead to this substitution product, and it could lead to these 2 elimination products. And this original carbocation can lead to this substitution product and this elimination product down here. So just considering the various carbocations that are possible and the various SM1 and E1 products that can result from those is how we can get to these various products. Of the elimination products, which would you say would be the major elimination product? Be the major elimination product. Now again, the substitution products are going to be the favorable one, and probably this is going to be the major overall because it comes from the most stable. It comes from the most stable carbocation, and because we do have a nucleophile present, that's why we do get a substitution. That nucleophile will attack the carbocation more often than not. So this will be our major overall. And of the elimination products, which do you think would be the major elimination product? I'm thinking the one where we can have a 1, 2, 3, 4, a tetrasubstituted alkene and that comes from the more stable carbocation. So both kinetics and thermodynamics are favoring this as the major E1 product. Let's try a few examples where we're looking at substitution and elimination competition. The ones shown here let's just focus on the SN2 and the E2 and see if we can decide which will be major. First of all, let's take a look at our starting material, our starting carbon compound, and see what we have. OTS. It's called a tosylate. That is a good leaving group. And what kind of carbon is it on? Is it on a primary carbon? It's not even on a primary carbon. This carbon has no carbons attached, so we just call him a methyl. So we have a methyl tosylate. And what are we reacting it with? We have the sodium means that I have a CH3O minus. And what do you know about methoxide? Now this methanol, what is this methanol doing here? Well, it's very common that when you're using methoxide as a reagent, you use methanol as your solvent. But because he is neutral and stable and less reactive, we're not going to consider him for our reaction. It's going to be the less stable, more reactive species that's going to dictate the path of this reaction. So what do we know about methoxide? Acid, base, electrophile, nucleophile. Well, it's a strong base. And it's a strong nucleophile. So what mechanisms does it have? These are perfect for E2 or SN2. So we said that, that alkoxides like this, like methoxide, is a perfect substrate to have this competition between E2 and SN2. So who's going to win in this case? If you have a leaving group on a methyl carbon, then it's going to be impossible to do the E2 because there is no beta hydrogen. So I'm expecting to do the SN2. That means backside attack the carbon, kick off the leaving group. So my methoxy group is going to now be attached to my methyl group. It's going to be a substitution, backside attack. Okay, we have another alkyl halide. This time it's on a secondary carbon, so this is a secondary leaving group. And what do you know about ammonia? What kind of reactivity does ammonia have? Is he strong, acid, base, electrophile, nucleophile? Well, he's a very good nucleophile, which means he would love to do the SN2. But is he a strong base? He definitely is basic, but he's not one of the strong bases we identified for the E2. He doesn't have a negative charge on it. Okay? Not a really, really strong base. So in the case of a neutral amine, our favorite reaction is going to be the SN2, which means backside attack. And tell me about the stereochemistry of that nitrogen. Since our leaving group is pointing out towards us, the nucleophile has to come in from behind. Let's keep our carbon chain fixed. And so now, instead of the wedge pointing down, we have a dash pointing down. Now what happens to that nitrogen when it gets a fourth bond? 1, 2, 3, 4. Nitrogen wants 5. It's going to be an N+. Okay, which means a lot of times we draw that leaving group in there because the bromide's not going to get very far. It's going to have an ionic bond with the ammonium. So a lot of times we draw it as this salt here as this product. Okay, who is DMF? It's another commonly used solvent in organic chemistry. It's an example of an aprotic solvent. And so a lot of these are, abbreviations or names you should be familiar with and get used to seeing them there. Even if we don't draw a solvent, all of our reactions are run in a solvent, so it's good to get some practice seeing those and recognizing those. In most cases, the solvent is not going to be dictating the mechanism that we choose, but of course it is possible, if the solvent is the only variation, that you're going to see a difference in the mechanism that you pick. Okay, how about this next one? We still have our same secondary leaving group, but instead of ammonia, we're using this guy, TBUONA. So this is Na+, so this is TBUO-. What do you know about TBUO-? TB-toxide. Strong, bulky base. So he loves to do the E2, not so good at the SN2 because he's so bulky. So even if it was primary, you wouldn't be able to do the SN2. This looks like perfect E2 conditions. Okay, so now we look at, for our beta hydrogens, we have some over here, and we have some over here. And so first we should consider regiochemistry. Where would we prefer to deprotonate? Well, we want to get the most substituted alkene possible. Okay, so we're not going to go to the end carbon. And then how about stereochemistry? Well, we know stereochemistry needs to be anti, but remember this is an acyclic structure, so we can rotate. It's not locked into any one hydrogen. And in fact, if it took this hydrogen, it would keep the carbon chain the same. And if it took this hydrogen, meaning it had to flip first and then do the elimination, it would give this product. So which of those two products do you think is the better product? How about stability of the alkene as a guide? Sure, the trans alkene is more stable. So that's going to be the one that we get. So don't be fooled by the conformation that happens to be presented. Remember that you can rotate the molecules and manipulate them around. These are in solution. They're mixing around. They can be any way they want. And so we're going to do whatever we can to get the most stable alkene possible, assuming that it's still anti-elimination. Okay, here are a few more. This one is sodium ethoxide and ethanol, so you could just abbreviate it as ETONA and ETOH. What do we know about ethoxide? Acid base, electrophile, nucleophile, strong base, meaning it could do the E2, strong nucleophile, meaning it can do the SN2. So how do we decide which is going to happen? We take a look at our carbon bearing or leaving group, and what do you see? Where's our leaving group? Well, there's a problem. What do you expect to find as a leaving group? Chloride, bromide, iodide, tosylate. Is hydroxide a leaving group? No, not a leaving group. So if you don't have a leaving group, can't do a substitution, you can't do elimination. Doesn't matter which, you can't do any of the four mechanisms that we've learned for SN2E2 or SN1E1, no reaction. Okay, we learned a couple strategies where we could make this reaction happen. If we had made a tosylate first, then we could do a substitution elimination. If we had a strong acid present, then it's possible to do a substitution. But that's not the case here. We have strongly basic conditions so that nothing's going to happen with that alcohol. Okay, same thing's going to be true in this next step. We have sodium azide and acetone. Azide is a very good nucleophile. It's not a strong base. It's a good nucleophile. Another nucleophile we should get used to seeing for the SN2. Okay, but because this is not a leaving group, again, no reaction. Nothing it can do. Okay, and how about our next one? We have hydroxide. Hydroxide is a strong base. It's a strong nucleophile. So this is a great example where we have our E2, SN2 competition. Do we have a leaving group this time? Yes, we have an iodide. So we're back to our alkyl halide. So we have a leaving group that we can get rid of. What kind of carbon is that leaving group on? It is a 1, 2, 3. It is a tertiary carbon, a tertiary leaving group. So what do you think? Is that backside attack? Is tertiary good for a backside attack? No way. Impossible because of sterics. So this is going to be all E2. And so now we have to think about regiochemistry. We have to think about stereochemistry. We've already identified our leaving group. Where is our beta hydrogen? Well, we have this beta hydrogen. We have either one of these beta hydrogens. This is very similar to a substrate we worked with earlier. We're going to want to eliminate one of the inside, one of the ones within the ring, so that we end up with this tri-substituted product, more substituted. So just a little reminder, we don't want to eliminate in this direction because that's going to be di-substituted. This is less stable. We always want to get the more stable alkene possible. Okay, and finally, here we have our same tertiary leaving group. And we have sodium cyanide. What do we know about sodium cyanide? Great nucleophile. Great nucleophile. Loves to do the SN2. Okay, is it a strong base? We have our list of strong bases. This is not one of them. This is a weak base, so it cannot do the E2. So let's take a look at our SN2, our backside attack. Does it look like a good SN2? Tertiary leaving group? No way. So guess what? We have a great nucleophile, but our carbon bearing the leaving group is too hindered. And it's not a strong base, so it can't do an E2 elimination. So this is another example where no reaction is going to happen. Now you might ask, well, can't we have the leaving group just leave and make a tertiary carbocation in this case and maybe do an SN1 and do the substitution that way? Well, here is one case where the solvent is going to come into play. The cases where we did see an SN1 reaction, like in the solvolysis reactions, we always had a protic solvent. And that's going to be true for a carbocation formation. It actually needs a protic solvent, like water or an alcohol. Protic solvents have an acidic proton. They're extremely polar, and they're needed to stabilize this extremely unstable polar carbocation. If you have an aprotic solvent, it's not going to be possible to form a carbocation. Now, you know, most textbooks aren't testing that much detail, but this is an example where, you know, really having an understanding of the details of the solvent capabilities is going to help us determine something about a mechanism. In this case, I was specifically asking you to compare E2 versus SN2. So with those restrictions, for sure, we could conclude that it's no reaction. So SN1 would be a good guess in this case, but it turns out that would not be possible either. Okay, so that wraps it up for looking at elimination reactions and considering their competitions with substitution reactions. Hope to see you again soon. Thank you.